Welcome to another video of Stat 420. In this video, we're going to talk about simulation in R, and we're going to look at the for loop as well as the replicate function. So simulation in R is really helpful in terms of just saving us time and also just kind of opening up more possibilities for doing some probabilistic thinking and modeling in ways that we couldn't do without computational software. So the first thing I'm going to do is a for loop to simulate what happens if I sum the results of rolling two six-sided dice. And by simulating this a bunch of times, I can get a sense of what results are most likely to happen. Now, this is something that I could certainly calculate probabilistically as well, right? So if I know that each of the six sides are equally likely to come up, I can actually list out all 36 outcomes, and I can count how many out of 36 add up to a roll of 2, 3, 4, 5, etc. So I could calculate these very exactly probabilistically. But as we'll see with different examples, sometimes it's not very convenient to do that. Sometimes the probabilistic calculation is very tedious, or sometimes it's just very difficult to even solve to begin with. So that's where simulation can really help us out, as it can do some simple or even complicated calculations for us almost immediately, and we can simulate it tens or even hundreds of thousands of times to kind of approximate what that probability distribution really is. However, I'm going to start with a very simple example that obviously we could calculate exactly, but let's go ahead and start with something simple just for example. So first I'm going to define my two dice, which are just going to be two sequences from 1 to 6. So if I define each of these dice, then this is kind of like I'm having my two dice of vectors of 1 to 6. And when I get to my for loop, I'm going to sample randomly one of these numbers, which is going to kind of simulate rolling the dice. And so now I'm going to go ahead and construct my for loop. I need to add one or two other things out here before I do that, but I'm going to go ahead and construct it first and then talk about what I need to do as I go. So first, I'm going to write for, and then in parentheses, I'm going to say how many simulations I want to do. And so typically, you would do something like I and then go 1 to however many you want to do, so like 50,000, like this. I could do that. This I is just a stand-in variable, as long as I'm not using it for something else. I is just going to iteratively go from 1 to 50,000 or whatever number I set here. And then in brackets, I'm going to say what I want to do at each step. So it's going to run through this loop 50,000 times, and this is what I want to do each time, is I want to sum up sampling randomly from D1. So I'm going to sample from D1 one time, and then I'm going to sample from D2 one time, and I want to add up those results. However, if I don't set this equal to something, if I don't assign a variable here, then every time this loop runs, it's not going to necessarily save the previous result, or at least it's not going to save it under a name for me to calculate later. It's just going to produce all the results. So what I want to do is save it under a name such that afterwards I can make a histogram of this result, right? So I want it to save under something. However, if I just say result and I don't say anything else, it's going to keep rewriting over it. So I'm going to have result continuously be just one value. It's going to be the sum, and it's going to change every time it runs the loop. So I want to have a different entry for each of the I iterations that I do, or I should say for each iteration, and I is going to equal whatever iteration I'm on. I want to add that next placeholder for results. And so this is the thing that I need to add up front, is if I define result here to represent some vector that's filling up iteratively, then result's going to have to exist first, or else R is going to be very confused because it assumes this must exist if it has a place. So I'm just going to set result equal to null. It's going to be empty, and it's going to fill up for however long I want it to go based on the loop here. Okay, so I believe this should work. I think I thought about everything. So I'm going to go ahead and run this. It's going to, in this case, it doesn't take long at all. So if I added more simulations, maybe I would have to wait for it. But already we can see a result where I can see how often I get each result. I could also run a table here, which might be a little bit more helpful as well. And I can see how often I got each of these different values. I can divide this by 50,000 to get a sense of what percentage of the time or what proportion of the time I got each value. Now, apparently this is a pretty simple loop to do, so I'm going to actually make this, well, let me do 200,000, and this might make me wait a little bit longer though. So I'm going to set result equal to null again, and then I'm going to start it over. In this case, notice that there is a stop sign for a little bit, meaning that it does have to take a second or two to calculate this, but again, it does do it pretty quickly there. Okay. Now, there is another function in R called replicate, and replicate is a more efficient design. So in this case, this isn't a very complicated loop, but the more samples that I want to do, or the more complex the loop is going to be, the longer this is going to take, and you're going to notice that in a lot of different situations. So replicate's a nice alternative to realize in a lot of situations that's going to work a lot faster. So I'm going to do the same thing with replicate, and so replicate looks like this. The first entry is how many simulations I want to do, so I'm going to do 50,000 again. And then I'm going to define what I want to calculate, and what I want to calculate is sample of D1, 1, plus sample of D2, 1. I'm going to go ahead and save this under a variable name as well. I'll call it new result, and this should calculate almost immediately, in which it really does. And again, I can do the same things that I did before. I can do a histogram, or I can do a table or something like that. And again, I can up this. I could even do, I'm going to do 500,000, and we'll notice that this is going to be really almost, well, maybe not quite so instantaneous. So it might actually be because I have my recording device running, so that might also kind of interfere with the normal processing. But normally it would do it almost instantaneously. But usually replicate's going to beat a for loop most every time. All right, so let's look at a different context now. So again, this is something that we would be able to figure out probabilistically in normal situations. But what about something that's a little bit more challenging to do probabilistically, like an unknown distribution? So let's do another dice rolling context, but this time I have a 6-sided dice, an 8-sided dice, and an 11-sided dice, and I want to know what outcomes are most likely to come up if I add all three of them up. So this is something that I don't necessarily know, and would be a lot more tedious to calculate. Certainly possible, but more tedious. So we have the same result here. This time I'm going to do it with replicate instead of doing a for loop again. So again, it's going to be kind of the same setup. I'm going to set this to 50,000. And then we're going to do a histogram and a table of the results. And we get these results, and we can see that very quickly. So obviously, the time it takes to write this code would probably go a lot faster than the time it would take us to do these calculations. So hopefully that convinces you that this has some value. And again, these aren't going to be exactly the case. So if I were to run this simulation again, by the way, so let me just do it again. I'm going to get another random result, and I'm going to look at the histogram results. You're going to notice that these numbers do not exactly match up. In some cases, it's pretty close. In some cases, there's a little bit more noticeable gap. So again, because it's a simulation, there is going to be a little bit of error. But the bigger we make this, so if I make this 500,000, I might have to wait a little bit of time here, but we are going to get some fairly accurate results here. And if you were to do this a couple of times, you would notice that the values are going to stay pretty consistent. So the more samples you can do, the more accurate those are going to be. Again, I can find probabilities related to this. So maybe instead of finding the probability for an exact value, I want to find how often I get a result below 10 or something like that. So what I'm going to do is I'm going to do the mean of, and I'm going to do triple results is less than 10. So if I do triple result is less than 10, by the way, it's going to essentially run my vector, and it's going to produce a bunch of trues and falses, where true if this is true and false if this is not. So if I take the mean of a vector of trues and falses, I'm going to get the proportion of times that this happens. So it means that about 15.8% of the time this is true, and about 84.2% of the time this is going to be false. So the mean function is really helpful in this case where I'm looking at a vector of trues and falses. It will give me that proportion there. And again, I could do this with any combination. This is a very simple true-false setting, but if you have any other curiosities, you could set up the same structure here. All right, so I'm going to do one other thing here, and that's going to be simulating a sampling distribution for mean differences. So when we think about a hypothesis test, so like a two-sample hypothesis test as an example, maybe what I want to do is, or well, actually what I do want to do is think about how often the mean difference that I observed with my sample results would happen by random chance if the two distributions actually had the same mean. So I can kind of simulate that here, where I'm going to do another 1 to 50,000 for loop. I'm going to randomly sample from this normal distribution, and I'm going to randomly sample again from the same normal distribution. And then I'm going to find the differences between my two sample means. So because I'm just doing samples, I'm probably going to have a difference between my two sample means almost every time. But if I look at the distribution of sample mean differences, they should be centered around 0. So I'm going to do that here. And again, we notice that my sample mean difference is centered around 0. Sometimes x1 is bigger than x2. Sometimes x2 is bigger than x1. But it does center around 0. I can do the same thing with replicate as well. So this isn't too complicated. Where I can, it's a little bit more complicated than the dice example, but I can still find the mean of my R norm sample minus the mean of another R norm sample and just kind of put it here after the comma. In this case, I put it on a separate line just so it's a little bit easier to read. So again, with functions in R, you can keep everything on the same line if you want, but it doesn't really hurt anything to just kind of split things up as you need to, just for sake of readability. So if I do this with replicate, I should get kind of the same looking result. It's a random sample, so it could be shifting a little bit, but it should give me the same general result. Now, I want you to compare this to the probabilities we'd get if we use something like p-norm. So we could calculate the probability of getting a sample mean below 0 or below -1 or something like that, given this information. So the distribution of my differences here should be a normal distribution of mean 0 and a standard deviation of something a little bit complicated, but it does come out to the square root of 0.72 if we follow the math for a two-sample standard error there. So I can find the p-norm, or I can use p-norm to find this probability exactly of how often I should expect my sample mean difference to be below 0, and it should be about 50%, right? I can also use my simulated sample mean differences to kind of approximate this, right? So this is not going to come out to exactly 50%, but it should come out fairly close here, and it does, right? So in this case, even though I have a function that can do this exactly, there might be a lot of cases where I don't have a function that does this. I'm looking at something a little bit more complicated. So I can always simulate kind of a sample result, and then I can calculate what proportion of the time I'm getting results below or above or between a certain value. So again, I could do a different value, how often I should get a sample mean below negative, or a sample mean difference below -1. And I can do the same thing with my simulated results, and it should come up fairly close there. And again, the more samples I do, the closer these two values should be. All right, and so one last thing for this video is I do want to show you a case where a for loop is appropriate, where replicate would be very difficult to do. I hesitate to say impossible because maybe there is a way to use replicate, and I just haven't thought about it. But I'm going to show you a case where it would be a lot easier for us to just construct a for loop, even though in a lot of these simulation examples, replicate would work a little bit faster than a for loop for just kind of simulating a sample and then doing one thing with it. So here's a case where I'm going to roll a die, and I'd like to know if I were to sample 50 dice rolls, how often I would get if I ran like a one sample z-test or t-test, or I guess in this case it's going to be a t-test, how often or what distribution my p-values are going to make if I'm comparing it to a null hypothesis of the mean should be 3.5. So if I roll a six-sided dice, the average should be about 3.5, right? Because I have 1, 2, 3, and then 4, 5, 6. But if I just take a random sample of 50, my sample mean is probably not going to be exactly 3.5. And if I were to run a t-test, most of the time my p-value isn't going to be terribly low, but every once in a while maybe it will be. So I'm going to take a random sample of 50 dice rolls, and then I'm going to calculate the p-value from a t-test. So I'm going to take a t-test with null set to 3.5. I'm going to extract the p-value, and I'm going to put it in this p-value vector here. And then I'm going to do that about 50,000 times, and then I'm going to look at the distribution of possible p-values that I get. So I'm going to run this. It shouldn't take very long. There's a little bit more in this for loop, so it does take longer than the previous one. And now I'm going to make a histogram of my results. And this might be odd to you because you might have been expecting a normal distribution or something like that, but if we think about how p-values work, this actually makes a lot of sense. Where if the null hypothesis is true and I really am sampling from something that has a mean of 3.5, then my p-value is just as likely to be 80% as it is to be 20%, right? So 5% of the time, I will happen to get a p-value below 5%, because that's what a p-value is the probability of getting a result this unusual if the null hypothesis is true. So in that case, my distribution of possible p-values should be a uniform distribution from 0% to 100%. But yeah, this is a case where a for loop is going to be a lot easier to construct because I need to run my sample and then I need to extract something from that sample. That would be a lot harder to do in a replicate format where I don't, again, I won't say it's impossible, but I'm not entirely sure how I would do that efficiently in a replicate. So this is a case where for loop would be a lot easier to construct.